Okay, ni hao to all you physics students out there. Welcome to our topic on uniform circular motion, and we're talking about motion of objects moving in a circle, but we're narrowing down to just those objects that are moving steadily in a circle. So if we looked at the Thunderbird's clock up there, we could look at the second hand ticking around, and it will take a minute every time for the second hand to do one full revolution. So that's an example of what we're looking at. So if we were to look at the speed of the object, we would see that it's always constant. However, if we look at the velocity, if you remember definition of velocity, it's speed in a given direction. So in this case, the direction is changing, and therefore we have a changing velocity. Even though the speed is staying the same, the velocity is changing. So what we're going to look at is the object moving in uniform circular motion actually accelerating? Because its velocity is changing, is it accelerating? So we have to look at our fundamental definition of acceleration, which I've got on the board there. That acceleration is how much the velocity changes per unit time. Alright? And to do that, we're going to start with our two velocity vectors. V0 is our starting velocity, and then V is our velocity at some point around the circle. Alright? So let's have a look at that. Okay, so these two velocities, you can see, have the same speed, but they have different directions. So what I want to do is actually see whether I can find out what the change in the velocity is. Okay, remember that little delta in the start of delta V means change. How much has the velocity changed? And to find the change in something, we just do a subtraction. V here is our final velocity, and V0 is our initial velocity. So if we subtract those two things, we will actually get the change in the velocity. Okay? If you remember back to your vectors work, you'll know, however, that we can't actually subtract vectors like that. If we were just dealing with the magnitude, say this object was moving 5 meters per second in the speed, then clearly 5 meters per second subtract 5 meters per second would be 0, and there would be 0 change of velocity. So we have to account for the direction. Therefore, we have to do what's called a vector subtraction. However, we can't actually do a vector subtraction. So how are we going to do it? All right. What we're going to do is we're going to add the negative of the second vector. So it'll look something like this. We're going to add the negative of V0. Right? Add the negative of V0. And we do know how to add vectors. Okay? If you have two forces acting on an object, say one force is this way and one force is this way, okay, downwards, then the resultant force is going to be diagonal down like that. And we know how to add them. Do you remember how to do it? Okay. V0 plus V, if we're adding velocities, for example, we would end up with VR, and R stands for the resultant, and we're using the tip to tail method. So we're adding the tip of one vector to the tail of the next vector. So essentially we're going to do the same thing here, but we have to add the negative. How do we do that? Well, we reverse the direction of our initial velocity vector. So if we want to make a vector negative, then we simply change the direction. So it was moving this way, but to make it negative, we flip it the other way and put the arrow on the other end. Now, we can use a similar method to the tip to tail method to add the negative of V0. All right? And to do that, we simply translate the negative v naught vector to the end of the final velocity vector. I'll do it down here so you can see. So I've got v and then negative v naught added tip to tail. And then what do? We go from where we started to where we ended, and we'll get our resultant. But, of course, what is our resultant in this calculation? Well, what we're trying to find out? We're trying to find out the change in velocity. Alright, so that's our resultant, delta v. Okay, so once we've got delta v, we've got the actual direction of the change in the velocity. Now if I do it actually on the diagram, on our circle diagram, hopefully you'll be able to see something a bit clearer. So, and there you have it. Delta v, which direction is it pointing? Funnily enough, it's pointing towards the centre of the circle, which brings us to the name of my YouTube channel, which is radially inwards. Okay, so the change in velocity vector is actually headed towards the centre of the circle, radially inwards. Okay, now why is that significant? Well, we can then go back to our original formula and connect it to the direction of acceleration, but we'll get to that in a minute. I just need to point out that if you're careful with your diagram, you'll see that in this actual diagram, the change in velocity won't actually be right towards the centre. And the reason for that is that the two initial points are quite a distance apart. And if we bring that distance closer and closer together, so the initial velocity vector and the final velocity vector come closer and closer together, if you're talking limits, it would be the limit as the displacement approaches zero, then you'll see that the change in velocity vector will actually get closer and closer to pointing exactly towards the centre, and we will have proper circular motion. Okay? So, let's look at the acceleration. Now, the acceleration vector is equal to the change in velocity vector divided by the time. However, we know that time doesn't have any vector nature, doesn't have a direction, it can only go forwards, right? So, if the change in velocity vector is radially inwards, what must be the direction of the acceleration? We can see if the time has no direction component, then the acceleration must be in the same direction as the change in velocity. In other words, radially inwards. Great.